Welcome to another video. I know I haven't uploaded in a while, but we're back. I've been kind of busy, but we finally have it back. So, today's video, we're going to be focusing on application of integration. We're going to be talking about this 'cause it's one of my favorite things in mathematics. And I really want to get straight into it and explain what this is. And this isn't really like an explanational video. It's mainly like for people that already know what the application of integration is. I will be uploading a video on what it is and what you use it in and the first basic steps. This is a video where it's a little bit more into it, more in depth. So if you know what application of integration is and you just need a little refreshment to see like, oh, okay, yeah, I do know what I'm doing here and that. So this is gonna be a really good video. So let's get right into it. So we have this graph right here with an equation on top. This right here is called an area under the curve, which obviously we all know that it is. And we have a point, the endpoints are -1 and 3. And if we do into like a revelational um, revolved, it's going to proceed to be a solid. So this right here produces a solid of revolutional um, when it's revolved about the x-axis. So it's kind of nice how it transforms into this once it's twisted up and you just make it 3D. I'm not the best drawer, so obviously it's not gonna be, the best. But anyways, let's get started to go ahead and solve this right here. So this right here, again, it's uh it's revolved um about the x-axis. So same points, same everything, -1 and 3. Okay, so the slicing method, we know that it's this specific um, formula. We use this method in Riemann sums, like development of the formula, like when it's used, we developed like the slicing method, so we know that it's this formula. The only difference with the disk method is that we know the formula for the cross-sectional area ahead of time. It is the area of a circle. This is given a following rule. So pretty interesting how you can also use this like in slicing method, but like it said here in one of the textbooks I'm reading, is that we know that formula for the cross-sectional area ahead of time. One of the rules that this method has, and I'm going to explain as simple as I can, is that you need to make sure f of x is continuous and not negative. So define R, for example, as the region bound above the graph of f of x. Um, so below the axis left by the line of x equals a, and on the right, which x equals b, which we're talking about here on the left line, this is equal to a, and this is equal to b. So that means that the volume is for the solid revolved is formed by revolving r around the x-axis, and it gives us this type of formula right here, which it will be v is equal to our integral b and a pi f of x squared equal to our bounds So square plus 1 square the x. So we can go ahead and expand this whole thing, which the thing is that what we need to do is we need to find like technically like multiply with our square and also expand in a way. So right here, since x is minus 1, going to give you x minus 1 to the power of 4 plus 2 x minus 1 squared plus 1, and we're going to have a squared here. The x, okay, guys. So if you're wondering how I got this here, because I feel like I didn't explain myself too well on how I got here, it's just like I already wrote it, but I think I'm gonna go further and explain on how I got it. It's just using normal algebra, which if you know your formula, a squared plus 2ab plus b squared, you should be able to do this just fine. So if you want to set this up as so we have x minus 1 squared plus 1. So if you want to set this up to a is equal to x minus 1 squared, and then b is equal to 1, you can just go ahead and proceed after that. So that means that our a, and you can plug this in this equation here. So if you want me to release a video of this normal algebra, I can, so you can get it better, and I will. So x minus 1 squared is equal to x minus 1, oops, fourth. It's 2 times 2 is 4. And then obviously our 1, which is times 1, because b is 1 right here. So since we have this here now, 2ab, you can replug this in a, and then also b again. You don't plug b in on this one, but you can plug a. But on this one, you will. So this was our first. Now we need to head to 2ab, which 2ab is going to be 2 times x minus 1 squared times 1 is equal to 2. That's this right here, 2 times 1, that's 2. X minus 1 squared. And if you want now, you can put them all together. So that'll be x minus 1 fourth plus 2 x minus 1 squared plus 1. And that's how you get your answer. Because b squared is just going to be, 1 squared. It's just 1. So that's how you get this equation right here. So you want to make sure you expand that the full exact way. So anyways, we can go ahead and continue now. Derivative of this first one here, 1/5 x minus 1, 5. The derivative of the second one is 2/3 x minus 1 cubed. And then the derivative of 1 is just x, the antiderivative of everything. Sorry for saying derivative, antiderivative. So now we can go ahead and evaluate, which is our favorite long way. So we can go ahead and use the PEMDAS, which that's going to give us our answer, which I'm going to have pi. We'll use our first evaluation, which is 1/5, put in 3 minus 1/5 plus 2/3 cube right here minus 1 cube plus 3. So now you can evaluate this whole thing. So right here, 3 minus 1 inside the parentheses is 2. And then 2 times 2 times 2 times 2 times 2, which is 2 times, 5 of them, is going to give you 32. 32, and it's going to give you 5th here. So, um, for our next one here, it's also going to be 2. So remember that it's going to be 2, and it's going to be 2 times 2 times 2, which that is obviously going to be 8. 8 times 2, that is going to give us 16, and I believe that should be one right here for this one, and it should be positive 16 over 3. And then after this, it's just going to be plus 3. So this is one of them right here total. And to find our second evaluation here, it's going to be the same exact thing. So now I'm going to do pi 1/5. This is going to be -1 minus 1/5 plus 2 over 3, -1, 1 cubed plus 4, -1. And now we can go ahead and evaluate this right here. So this right here is going to give us, the first one is going to give us -32 over 5. The second one is going to give us 16 over 3. And then the last one, obviously, -1. So using our f of b minus f of a. Yes. So after that, you can now go ahead and evaluate. 32 over 5 plus 16 thirds plus 3 minus 32 over 5 minus 16 over 3 minus 1. So that thing looks terrible. So now, when you evaluate this whole thing, and you can go ahead and do it, you're going to get 4, 12, 15, and make sure to put your pi and make sure it's units cubed. And this right here should be your answer for what we did with our application of an integral. Um, if you want to go ahead and see and recommend more videos, in the comments, that would be absolutely amazing. This was fun and very long at the same time. Next video, I do want to talk about more application of integration, um, and just keep going up after that, like Taylor series, Maclaurin series, sequence series, and um, all that cool stuff. But if you need to go over like any basics, for example, like factoring, like what we did here, where I explained all this right here using a squared plus 2ab plus b squared, I can go ahead and do that, just, kind of like algebra, so you can be more sufficient on what you're doing. Next video, I do want to talk about, I believe, applications to L'Hopital and integrals, not applications to integrals, just technical L'Hopitals and integrals. Um, so how to use this. This right here would help you a lot understanding very easy integrals, not hard at all. But obviously this over here, it's more advanced, because I mean, it's obviously a calculus 2 session. So thank you for watching this video. Brain Gears is out.